So happy Thursday, everybody. Are there any questions before we start? Somebody asked me a question like, are you allowed to use more than one tool for assignment 2? The answer is yes, you are allowed to use more than one tool for assignment 2. Yep. And probably I'm picking up psychic waves actually all of a sudden. Some of you are wondering but are too afraid to ask about assignment 1. Like if I've done with those, assessing those. Right? Am I right? Don't be afraid to ask questions. What's the worst thing that could happen? So the answer is yes. I finished assessing assignment 1 just before I gave a lecture earlier today. So I finished, and I was, I just didn't have time to enter the scores into Blackboard yet. So I went and ate very quickly, then gave a lecture, then went back to my office, got ready for this lecture, and now I'm giving this lecture. So I will hopefully enter the scores on Blackboard before Monday's lecture and then have the feedback forms and everything.
How are the results?
Bad. Really bad.
They look okay. I guess I would have expected a little higher, but they look reasonable. I'm guessing the average is somewhere in the 60s. That's my guess. The people that struggled were the people that either didn't finish it, some people didn't finish, or didn't read the instructions from start to finish. They just didn't know exactly. It's clear. I can tell when I'm looking at the assignment if the person finished or if they read the instructions or not. So if you finished and you read the instructions, then you probably did quite well. Otherwise, you might not have done so well. That makes sense, doesn't it? Here's the attendance. Any other questions about assignments 1 or 2? So assignment 2 is more difficult than assignment 1. It's very important to read the instructions. And the thing with assignment 2, there are some very valuable hints in assignment 2. There's a list of hints. You have to read those, otherwise you won't be able to do the assignment. So just as a warning, that's not optional. You just won't be able to do the assignment, I think, if you don't read those hints.
Deadline?
The deadline, I'm still thinking about that. Yeah, I'm still thinking about that. But yeah, the deadline will change. I can just have a quick look at my calendar right now and see if I experience any psychic activity. So the current deadline is the 28th, if I correct.
29th.
The 29th,
Yeah.
the current deadline. Okay. So I guess I can move it to the 2nd of December, if that makes everybody happy. Does that make everybody
No.
Why is that? Why is everybody laughing? Because you have other deadlines on the 2nd of December, or
We have 7 deadlines before end of the semester.
do you have deadlines on the 2nd of December?
I think so.
One more assignment.
I think so.
You do have 3. The 3rd assignment is optional.
Oh, okay.
Yes. The 3rd assignment is if you are unsatisfied with your scores on either assignments 1 or 2, you may do assignment 3 to try to raise your scores.
So is it similar to assignment?
You could find a copy of it on Blackboard from last year, but I don't think it's going to change. Yeah, so you can see it on
Is it similar
Blackboard.
to 1 and 2?
No, it's completely different. Assignment 3 is you're given a research paper, and then you have to write a 2-page summary of that research paper based on a very specific set of extraction principles. Yeah. So everybody was excited about that idea of the optional
I
assignment
think
3.
it's a good idea. It gives people the option.
Exactly. Yeah, I like it too. I like it. Excuse me?
At least that we
Yeah.
have the option to.
It's I wouldn't, it's completely different. Assignment 1 and 2 is quite different, I think, and assignment 3 is quite different from the other two as well. The variety in this module is just amazing. Any other questions? I remember when I was a student, I remember, like, I failed a coursework, right? And I had a scholarship, and the conditions of the scholarship were, like, you have to get this grade or above, or your scholarship gets terminated. I failed a coursework, and I was really upset, and I thought, oh my gosh, my scholarship might disappear. Is anybody else under those conditions? Okay. And the professor said, he's retired now. He said, oh, if you want, you can resubmit the assignment that you failed to get and I'll regrade it. And I was very, very grateful for that. So I pass along the charity generations. I failed the second time too, but no, I'm just kidding. No, I didn't. It was the very first it was one of my very first assignments during my master's degree. Very, very beginning. It was one of the very first assignments in databases. And I underestimated how difficult it was. I still remember the assignment. I still remember it. Assignments are so much better than tests. Tests, you just forget them, right? You forget them like within an hour of taking them. But it's courseworks. I remember a lot of courseworks. I remember them. They're more interesting learning experiences.
Are you planning to cancel our exam?
If it was up to me, I would cancel the exam and have everything coursework. Yes, if it was up to me.
It's not up
Yeah.
to the lecturer.
It's not up to me. It's not up to me. Things would be a lot different if it was up to me. The election results would be a lot different. Yes. Lots of things. I have a different attitude than the majority of anybody, I think. Yeah.
So who did you vote for?
I voted for Hillary Clinton. Yeah. I thought she was gonna win. I thought there was no doubt. I
Yeah, everybody thought that.
Everyone
Yeah.
says that.
yeah. So, yep. If my energy is a little bit off today, that's the reason.
Oh.
Yeah. I'll just say this one thing. The basically the bottom line is how well can you manage your pain? That is the bottom line. So everybody has some pain management strategies, and some are healthy and some are unhealthy. And it's the question of who has the healthy pain management strategies and who has the unhealthy ones. Yeah. That's what life boils down to in a few sentences. And yeah, some people have unhealthy pain management strategies, to say the least. Okay, so this is an example, by the way, of what we're talking about. Some direct volume visualization, so that's a tornado. And you can see that there is a tornado, but there are no explicit surfaces there, are there? They're not explicit surfaces, or they're surfaces with a thickness, right? They're not binary surfaces anymore. They have some thickness, they have some transparency that's changing, and so on. And that's also the time dependence data right there as well. It's changing over time. So it's more difficult to generate this kind of imagery or kind of visualization with traditional surfaces. Any other questions before we get started? If I get some psychic wave signals, I will let you know.
No.
The notes. I think we're just going to continue on from last time. I do have leftover notes. Was anybody missing from Monday that needs the notes? So these are extras for people that want a second copy or missed Monday's handouts. I also have extra copies of assignment 2. Does anybody want extra copies of assignment 2? So let's look. So we talked last time. We had a lot of terminology, didn't we? A lot of new terminology last time. We introduced the idea of ray casting. We talked about sampling. We talked about ray functions. And then we looked through examples of ray functions. Those are all ways to sample the data, the volume data. And what the results look like when we do that. We went over this term classification. And then we looked at this term called a transfer function. That really should be called something like information transfer function. And then we looked at an example of a so-called one-dimensional. It's kind of confusing idea, but it's called one-dimensional because data is mapped to color and data is mapped to opacity. But in fact, there are 2 dimensions. There are 2 visualization dimensions, the color and the opacity. But there's only one data dimension, and that's the scalar value. And you can get lots of different pictures depending on how you play with your transfer function, which scalar values you decide to map to red, and which scalar values you decide to map to green, and maybe which scalar values you decide to map to blue, and so on. Right, and this is the same volume data, but with different transfer functions, right? Transfer functions are usually interactive, right? So you can update them interactively and see the results changing interactively, which is part of assignment 2. Right, and there are some more examples, and this is where we stopped when we got to gradients. So this is another term. Anybody already know what a gradient is? I think you all know what a gradient is, actually. You might not have heard the term gradient used, but if anybody here lives in Swansea, you know what a gradient is. Because Swansea is on a gradient. It's on a hill. The whole city is on a hill. Anybody know Constitution Hill? That's a good one. That's a serious gradient. If you haven't seen that in Swansea, check it out. Anybody cycled up Constitution Hill? I cycled up just to see if I could do it, not for any reason. It's a good exercise. So those are physical gradients. A hill is a physical or geographical gradient. It's a slope, right? A geographical slope. But what is the gradient in terms, we look up the term gradient in the dictionary, we see different definitions. The degree of inclination or the rate of ascent or descent in a highway or a railroad or in Swansea, for example. Another definition is an inclined surface, grade, or ramp. Right? In physics, it is the rate of change with respect to distance of a variable quantity as temperature or pressure in the direction of maximum change, a curve representing the rate of change. In mathematics, it's a differential operator operating upon a function of several variables, results in a vector of the coordinates of which are the partial derivatives of the function. Has anybody taken calculus in here before? Nobody's ever taken calculus?
High school.
In high school, you took 2 semesters of calculus. Anybody else ever do that? I took several years actually of calculus. We also did it in high school. Yeah. So gradients are all about the transitions. From a data perspective, they're all about the areas in which the data changes from one spot to another, right? Gradients are also boundaries, right? If we have a ray function traversing the volume, we're interested in the gradients, where the density of the data transitions from, say, air to soft tissue or skin. That's a steep gradient, right? Gradients are associated with changes, right? And in the case of volume rendering, we're interested in large gradients, data gradients. So those changes in values over a given distance. And the higher the change, the higher the gradient, the more interesting that area is. Right? So gradients emphasize transitions or boundaries. This is trying to illustrate that idea. So here's a set of data, and it has a different value than the white, and so the gradient is pointing in this direction. And same here, the gradient is pointing in this direction. Here, the change in data value is bigger, right? This is darker than this one. So the gradient vector is bigger. The change is bigger, the gradient is bigger. So gradients are a vector, right? So we're gonna introduce this more confusing or advanced concept called a 2D transfer function or a gradient-dependent transfer function. Remember, we had the transfer function where data value is mapped to color, and then the same data value is mapped to opacity. Well, this time, opacity is mapped to gradient magnitude. So that is what we're trying to demonstrate or illustrate here. Opacity is a function of scalar value and local gradient. So it's 2 things, right? These 2 pictures are supposed to be the same. This one is drawn in PowerPoint, and this one is taken from the original paper that this idea is based on. So here, this axis represents increasing scalar value in the volume, right? It's the same as this axis. This axis, this y-axis, we could call it, represents the gradient magnitude of the data. So the higher the gradient magnitude is, the farther up the axis we go. And then this axis that represents opacity. So what the author is trying to convey is that the higher the gradient is, the higher the opacity is, actually, in this transfer function. And that's the idea. And then the color is mapped depending on the scalar as well. So color is mapped to scalar values. Opacity is mapped to gradient magnitude. Right? The greater the gradient magnitude, the higher the opacity. And that means that places or regions or surfaces with high gradient magnitude are visible, highly opaque, and areas of no change are invisible. And that's similar to actually the image that we saw already. That's consistent with the image we just saw in some ways. So uniform areas become less visible and high transition areas become more visible. And that was true about the tornado example that we saw in the beginning as well in the little video. So these are all the terms we need to understand the next algorithm, the ray casting algorithm. So you have to know what a ray function is, you have to know what sampling is, you have to know what a transfer function is, and a gradient, and then a 2D transfer function in order to understand this algorithm called ray casting. And it's an image order algorithm. Just a little note on terminology. So if you've taken computer graphics, which some of you have, you've heard this term ray tracing, which is a very common computer graphics technique or algorithm. And we're not talking about ray tracing, we're talking about ray casting. Can anybody say what ray tracing is? That took computer graphics. Are there any people that like, I don't know, Toy Story and all the Pixar films? Right, all the Pixar films. Does anybody watch Pixar films? Wall-E is probably the best one. Has anybody seen Wall-E? That's the best Pixar film, isn't it? Yeah, it is. They're all using ray tracing. Have you ever wondered about that? Oh, how did these movies get made? Yeah, it's interesting, isn't it? They're all using ray tracing. We're not talking about ray tracing. Ray tracing is an algorithm to compute the accurate lighting and shading of a three-dimensional scene. That's what ray tracing is. And the scene is composed of surfaces. Right? And the surfaces are composed of triangles. Right? That's a traditional computer graphics topic. Here we're talking about ray casting. And ray casting only involves a single ray, generally speaking, from the view plane through the volume. And it's sampling a volume. It's not hitting a surface and bouncing off the surface and collecting lighting and shading conditions from the environment. It's just traversing the volume and sampling the data as it traverses the volume. So we're talking about ray casting here, which is not exactly the same as ray tracing. So that's what this surface is about, right? So casting a ray through the volume, this is ray casting, right? We have a volume of one-dimensional values defined in 3D, right? So we cast a ray from the image into the volume. You've seen this already, right? And as the ray traverses the volume, it generates an intensity profile, which is the sampling. It's a sampling profile, right? It's generating a graph of the samples it encounters along its way through the volume. Technically speaking, it's a half of a ray. because it has a starting point and is just pointing in one direction. Right? A full ray would be pointing infinitely in both directions. So this is what the algorithm looks like. Does it look familiar somehow? If we draw a diagram of it? Yeah, it does look familiar. Why does it look familiar?
I remember you told us the same graphic before. I prefer you picture.
Looks familiar.
Yeah, it looks like the conceptual VolVis framework a little bit, doesn't it? The volume visualization pipeline. And that looks like the visualization pipeline. And they do correspond to each other. It's not random. You could call this a specialized version of the volume visualization pipeline. And you can call the volume visualization pipeline a specialized version of the visualization pipeline. So it's even more specialized. This is the most specialized version. So the pipeline gets split into two halves. The input is voxel values on a grid. There's a shading computation that assigns voxel colors to all the voxels. And there's a classification operation. We talked about classification very briefly. And that assigns opacities to all the voxels. So the voxels get assigned colors and opacities. That's the first step. That's I don't know if you could say that's really the that's a visualization mapping phase. That's what that corresponds to. So once we have the voxels set up with the colors and opacities, we cast rays into the volume on a pixel by pixel basis, right? An image order operation, the ray casting, which is also like a resampling. And at the pixel, so at the pixel level, or the ray level, let's say, if we cast a ray into the volume, it's going to collect or sample the voxel colors. And the voxel colors get added together, right? And we get this collection of sampled colors. And the same is true about the opacities. So we cast a ray into the volume and sample the opacities of the voxels, and they accumulate on a per pixel basis, right? And they're all added up together. That's called compositing. And then the result is that every pixel has a color and an opacity. That's a summary of the algorithm. Right. We can talk about it in a little bit more detail, right? So this is step one, this part, right? Voxel shading. So the voxel shading is using this two-dimensional transfer function, right? So for the sample values, we have along the x-axis the voxel values. They're all the data samples along the voxels. Those are mapped to color, right, and shading information along this axis. And then for the voxel classification, that's where the gradient magnitude comes in. So that the higher the gradient magnitude, the higher the opacity, right, to emphasize the transitions or the boundaries. This is very arbitrary, so you can pick any color map you want. It's not, you know, this is something that can change. The color map can change. This tent function, by the way, this is supposed to look a little bit like a tent. It's not that clear. because we don't have 3D that we can just rotate here. That's not so fixed. So the higher the gradient magnitude, that's the symbol for gradient magnitude, by the way, the higher the opacity, and that doesn't change. But the colors that you decide to map the samples to can change, right? You can change the color maps and so on. So that's the step, the shading and the classification. Then the next step is this ray casting or ray sampling, which this is what this slide is about. Now, we talked a little bit about this already, the sampling. We talked about different ray functions and how we could sample the data in different ways. And at that time, we talked about first hit, maximum intensity projection, averaging, and compositing, right? And we made the analogy with food. We can do the same. This is the same discussion, or a very, very similar discussion. How do we sample the volume data with a ray, right, when we cast the ray? And there are different ways to do that. This is an illustration of regular sampling in 2 dimensions. We cast a ray through the volume, and we sample the data, or we extract the data value at positions that are evenly spaced. The space between these is even. Now, the ray is at an angle. Right, so when we want to sample the data here, there's no data here, actually. The data is stored at the corners, or maybe in the center, it's possible as well. So to derive the data there, we have to use interpolation. Right, so we interpolate along one axis and also along the other axis, and in 3 dimensions, it's trilinear interpolation. Remember that? That was from at least a week ago now. And the same is true about all of these samples, right? This one happens to lie on the edge, so there's only one linear interpolation here and one linear, but the other ones are in the middle. So there's at least, in this illustration, since it's 2D, it's a bilinear interpolation, and 3D, it's the trilinear interpolation. That's called regular sampling. Another one is scan conversion, and that just takes the value at the center of each cell. So you could store a data value at the center of each cell and use that. And then there's one that's sort of like halfway in between. At using the data samples at the voxel intersections or along the boundaries. So here we have an intersection, a voxel intersection along the edge. Same here, and same here. Here we've hit an edge again, so we grab a data value, we sample the data. Here we have an edge, so we sample the data. And every time we hit an edge, we take a data sample. Does everybody see that? So the space between data samples here is actually uneven. It's changing, right? Here, this space between these samples along the ray is constant, but the space between sample values is changing, because here we're taking these two, here we're taking these two centers, but look, that distance has changed right there. Can anybody see why we might have these 3 different sampling functions? Where did the attendance register go? Hiding back there, hoping to stay safe. It's nowhere it's safe. Anybody know why we might have these 3 sampling functions? Any guesses? Okay, here's how about Jordan Collier? Did I pronounce that correctly? You thought you were safe all the way back there. Oh, I'm safe back here. What do you think, Jordan? They do provide different results, that's correct. How do they provide different results?
Well, I kind of want to put it into words, but I can't. I suppose, would it give you like, obviously putting in different data, so would it give you different types of visualization to like, so one could visualize like air, one could visualize like solid material.
You're getting kind of warm. Anybody want to help out Jordan? Does anybody feel his struggle and want to like jump in and help? I feel your struggle, Jordan. I'm going to help you. Anybody else want to take a stab at that? Actually, the answer, in some ways, the answers to every questions are the same. Every computer science answer is the same. And the question is always the same. It doesn't matter which module you're in, which question I ask.
Really?
Huh?
All the coursework.
What?
All the coursework as well.
All the courseworks. Yes. Yes, all the courseworks, all the tests. It's almost always the same.
Really?
Yes.
I'm just thinking that the intensity of the overall sample is not same in everywhere. That's why we are taking 3 approaches.
Getting even closer. Yes, yes, you're on the right in the right direction. Everybody's excited by that observation that it's always the same. It is always the same. So you can remember this for the rest of your life. For all computer science algorithms, there's always a trade-off between quality, speed, and storage space. Those are the 3 factors. So all algorithms are trying to optimize one of those 3 things, or 2, right? If you increase quality, you lower the speed, right? You might be able to increase quality, keep the same speed, but also increase storage space. So this is true about every single algorithm in the universe. It's these 3 factors. So whenever somebody asks you a question, you can be, okay, are we trying to optimize speed, storage space, or quality here? And which one's going down at the expense of the others? So congratulations, you got the answer for every computer science question algorithm for the rest of your life. So that's what we're trying to. Here we're trading off. We're not talking about storage space necessarily. We're just trading off computation time and accuracy. So here we have the highest accuracy, but the slowest computation. Here we have the fastest computation because we're not interpolating. We're just taking the value at the center. But the lowest accuracy because sometimes we get this big gaps. And here we're trying to make a compromise between minimizing small, the gaps, so that's the biggest gap. But the interpolation is always along the edge, so it's a little bit faster and easier. So that's the idea behind that. It's kind of interesting, isn't it? Did anybody find that interesting? That for every algorithm in computer science, it's one of those things being optimized at the expense of the others, right? So when somebody says, "Oh, I have an algorithm with a perfect accuracy that runs at 20 hertz," say, "Oh, that's great." but what are the storage space requirements? Like, I know there's something going on. You don't even have to know the details. You could already say, oh, and look very smart in the process. So voxel-based versus cell-based rate traversal. So that's just sometimes the values are stored at the corners, and those are cells. And if the data values are stored at the center, they're voxels. Right, and if there's interpolation involved, right? If there's a three-dimensional interpolation, that means there are actually 7 individual linear interpolations. If you can imagine a cube, right? There are 4 interpolations along the 4 edges, the z edges of the cube in the z direction. And once you have those 4, you can do 2 along the y axis. And then when you have those, then you do 1 along the z axis. That's a good exercise in spatial reasoning. Okay, and remember, we're still talking about this algorithm, right? We talked about step 1, step 2, right? And now we're talking about compositing. Step 3. What does that mean, compositing? The sample-by-sample accumulation of color and opacity along an array as it traverses volume data. That's the definition that I looked up. Well, I looked up the definition of compositing and I couldn't find it, so I made this definition. Probably if we looked it up today, I looked it up a few years ago, we would find a definition in one of our favorite books. But at the time, I didn't see a definition given in our favorite books. So that's pretty straightforward, right? Here's another term to make life a little more complicated. It's called a kernel. And to make life really complicated, it has more than one name. So a kernel can be called a convolution kernel, and it can also be called a convolution filter, which means 1 or 2 dimensional images that are used to compute the weighted average of a pixel image. That's from the OpenGL programming guide. We're going to talk about this more. Another nice way to think about a kernel is a weighted average. So I would write that down, right? Weighted average. So compositing can happen from back to front. So you add up the sample colors and opacities, starting at the back and working your way forward. Or you can go from forward to the back, like adding them up. And that's what the formulas look like for adding up. This arrow really should be an alpha, the alpha character, but something went wrong with the fonts, the PowerPoint fonts.
We have to memorize this formula.
No, you won't have to memorize those formulas. No. Okay, I have demos of back to front and front to back compositing. And this is what ray casting looks like. By the way, these are some images of ray casting. Right, these are the images you can generate, so that they look very familiar. Right, and we saw the video of this tornado at the beginning of the lecture. Right, and there's a visible human. And those are some more images, ray casting images. Right, and the full details of the algorithm are in this paper, which is also on Blackboard. And you can also read more about this in this book chapter. Are there any questions so far before I do the ray casting demo, so to speak? So let's see if I can get that. See if I can get that. That going. Is that the one I want? This one. You can see that this machine is not optimized for speed in any way, shape, or form. But it's kind of old. Any questions while we're waiting for the PowerPoint to start up? It's kind of, I think probably, it's slow on purpose, to build suspense, because it builds tension and some suspense and excitement. That's how you get the audience excited, through tension and suspense. Okay. Cruising right along. I hope it works. I guess I'm going to get a message that says you need to update your PowerPoint. That's a different presentation. The story of Sally, which I'm sure you're all wondering about. Not right now. Check for updates. That's going to take a long time if we do that. That's another exciting presentation, by the way. Let's try this one. Not right now, thank you. So, let's see if we can get this bad boy to work. Okay, so this is a demonstration of ray casting. I think it's going to work. This is a ray being cast into the volume, and here we're checking opacity. Here we're compositing color and opacity, and this is the volume data that we're trying to visualize. So there's the ray being cast right into the volume, and it hasn't hit anything yet, so we haven't added any colors and opacities together yet. There we proceed into the volume, right? We're sampling the volume. And then
following any trends, front to back or back to front?
This is, what do you think this is?
Back to front.
This one's front to back,
Front to back.
because we're going from the front.
Okay. All right.
It's a good question. I forgot to mention that. Hopefully you can see that ray going from front to back. Oh, and then we hit something. So we start sampling the data, and we have a sample color, and we have some non-transparent data. We keep going, and we sample the color, and the opacity is increasing, by the way, of that pixel. This is the opacity and color of a single pixel, right, on the image plane. And we keep sampling. We keep going through the volume. At some point we hit 1.0, which is the maximum opacity. that means the opacity can no longer change. And if the color and opacity can no longer change, we can terminate the ray. But and then we do that for every pixel, right? We do that same process, and we accumulate the color and the opacity. And that's what, that's a demo of what ray casting looks like. At least so you get some idea. It's pretty exciting, wasn't it? I can feel the excitement.
I have a question.
Oh, great.
It's not a correct question, but what about to change the place of color and opacity? First, it will start with color, and then second, opacity. So, what's the result will be?
It doesn't matter. It doesn't matter. If you remember the pipeline, they're being done in a parallel way. So you could have them on either side. It doesn't matter which one's first. Yeah, they're done in parallel. But you always want to test the opacity of the pixel, because if the opacity reaches 1, the maximum opacity, then you can terminate your array. You don't have to keep sampling the opacity, because you can't change the one. You've reached the maximum, so you can terminate the array and then move on to the next pixel. Yeah. Okay, are there any other questions? I guess we'll stop there then.